Audio Jungle. Audio Jungle.
So what is burning rate, right? It is very special parameter, burning rate. Burning rate. So basically the burning rate is defined as the recession of the propellant surface in direction perpendicular to this burning surface per unit time. Okay, and why it is important? Because based on this burning rate formula, that gate question they had asked. Okay, and and this is also called burning rate or burn rate. Okay, burning rate or burn rate. Or burn rate. All right, so basically this burning rate, if you say dependency of this burning rate, so it will depend on the propellant composition. What are the composition if you are talking about the solid propellant? So as I explained in my first lecture only, oxidizer and fuel we have to just convert in solid format and will mix and it will convert into solid format. So that solid propellant might you have seen somewhere in lab, or right? So it is actually the burning component. So for burning with the fuel or hydrocarbons we require oxygen, right? So that's the reason oxidizer and fuel I am saying you need to convert in such a way you can make finally final component will be a solid component, that solid propellant. Okay, and in case of liquid propellant you have seen that two vessels, one for fuel and one for oxidizer, and it will be the fuel tank, and as the name liquid propellant, so fuel and oxidizer both will be in liquid form. Okay, but in case of the solid propellant, both fuel and oxidizer you have to convert in solid form, and finally the product will be the solid product, and that's the reason it is called solid propellant. Okay, and so what is the propellant? Propellant is only the burning components, and propellant is basically combination of oxidizer and fuel. Hope it is clear. So that burning rate, it is depending on the propellant compositions, at what rate you have added oxidizer, at what rate you had added fuel, that percent in terms of percentage you can say. Okay, so that is the composition, because two types of the composition will have homogeneous and heterogeneous. Okay, second is what? Combustion chamber pressure. So this burning rate also depends on the combustion chamber pressure, just like in jet propulsion also, that mixing of the fuel and burning of the fuel in combustion chamber for the jet engine I am saying, it also depends on the combustion chamber pressure. That's the reason we require compressor to increase the pressure, to increase the temperature. Whatever the products it is, air is what going to enter in combustion chamber, that air should have very high pressure and very high temperature. Once you inject fuel, then fuel and air will start burning. So there also burning time or burning rate is depending on the combustion chamber pressure, and here also the same thing. Third point will have an initial temperature of solid propellant prior to start, then combustion gas temperature, then velocity of gas flow parallel to the burning surface, and motor motion, acceleration and spin induced grain stress. So these are the few factors, and they are asking question for 1 mark, so better will write this. Okay, this is the only theory part here in this rocket propulsion. So basically burning rate, so burning rate is defined defined as the recession of propellant surface in direction perpendicular to this burning surface per unit time. Okay, so what is the mean of the uh, perpendicular to this burning surface? I mean the recession of propellant surface in a direction perpendicular. So that meaning is very simple. See, if you have the propellant, so two types of the burning grain we have. One is side burning grain and another is what end burning grain. Okay, so if you say end burning, so this is the simplest cylindrical grain in which combustion takes place across the transverse cross section of the chamber. Hence it sometimes called cigarette burning grain. Cigarette burning means it will start from one end and it will continuously move and it will end to another end. That is the cigarette burning. Okay, so that's the reason end burning grain, because it is starting end to and it is going to end at the end. So end to end burning called end burning grain. Okay, and that's the reason sometimes it is also called cigarette burning grain. Grain in the sense that products, that propellant, that products, that composition of fuel and that oxidizer, that composition called grain. Okay, it is generally used for low thrust, low performance rocket engine with long burning time, as it is limited by particular cross sectional burning surface area. So this is called in burning grain. Okay, it is, I think, little bit going to extend. So two types of burning grain we have. So let me finish this. Burning grain, only diagram I will draw so it will be clear to you. Two types of burning grain we have, and then we'll go for the final formula. Final formula will not derive. Okay, it directly I will give to you. So two types of burning grain we have. One is called end burning, end burning grain, and another is what? Side burning. Okay, so if you go for the end burning, so that diagram I will go, so by diagram only you can understand. So end burning, this is also called as cigarette burning. Cigarette burning grain. Okay, so now if you have propellant here, see, just say this is the propellant, and propellant is what, somewhat like this. I'm talking here solid propellant. This definition, burning time, burning rate and everything, it is for the solid propellant. Okay, whatever I'm defining, it is for. So this is what propellant. So end burning means it is going to start here. Okay, this is called end burning. So it is, burning is what is started here. Burning started here and it will move in this direction. Okay, that's the reason it is called cigarette burning. Okay, that's the reason it is called cigarette burning. See, cigarette burning, no? So here that burning is started like this and it will move in this direction. It is called in burning. Only diagram you need to understand, that's all. This is called in burning. end burning. Okay, and in this case, if this is the way, then that basically this type of burning condition you will apply where the low thrust required, okay, and low performance rocket engine with long burning time, because it will take long time, because it's a lengthy, okay, if it is lengthy, so obviously it will take time to burn completely. So with long burning time, with low performance rocket engine, with low thrust rocket engine, this type of burning you will use. And here basically it is limited by particular cross sectional burning surface area. Cross sectional, why I am saying, because if you say, so this, if you get the surface area, so surface area will be here like this. So, and in this way it will move from end A to end B surface, and it will move from A to B. So this type of burning called in burning. Now going for the side burning. Okay, what is the side burning? By the word only you can understand. Suppose we have the propellant, and this propellant is what, like this. Okay, this is the cross section, you can see. If I want to draw for the side burning, so side burning you can show by this way. This is the side, okay, and the burning started like this. This is called side burning. And we have combustion products here. This is now combustion products. Okay, combustion products, and our flame will move in this way. So this is what flame front or flame front or flame motion, and here this burning rate R dot you will show by this way, and here the burning rate you will show R dot by this way. R dot. This what we had started burning rate or burn rate. This burn rate is noted by R dot. So the whole definition, like theory, it is coming under burning rate. Okay, and from long time we are talking, we'll see what is the burning rate. So now you can understand what is the burning rate. So burning rate or burn rate, two types of burning we have. For the grain, okay, grain is nothing but it's a composition, that products what we have, that oxidizer and fuel for the solid propellant. So for that product, how that burning is what possible. So two types burning possible. One is what in burning, another is what side burning. So this is what side burning. Okay, now if you want to calculate that mass of the propellant, the mass generation rate due to burning of the propellant surface in combustion chamber, so how to get this? So for this we have a formula, and direct I will write this formula. So I can write, because the combustion products we have now here. Okay, so this combustion products, so what is the mass generation after burning? What is the mass generation? Mass generation rate due to the burning, of the propellant surface in the combustion chamber. So this value will be mass generation rate. So after burning that combustion products you may get, right, this combustion products you may get. So what is the amount of this? So this amount of this is nothing but, I'm just going to write generation rate. If I'm saying it is m dot, if they are saying only mass, then it will be mp, but this is the mass generation rate, so m dot p. Okay, and obviously propellant mass generation rate you will get, so m dot p, or sometimes it is also denoted by m dot g. Why g? Because it is now gas, because oxidizer and fuel in propellant, I told you propellant is what, it's a combination of oxidizer and fuel. So in few books you may get m dot p, it is okay directly, but in few books you may get m dot g for gas. Okay, and it is gas or that amount of the product generated. Okay, so m dot g, and this value will be, this value will be rho p, density of the propellant. This is the density of the propellant, okay, into r dot. This r dot is nothing but burn rate, okay, into AB. Okay, so AB is what? Burning surface area. Burning surface area. All right. AB, I can say AB is nothing but burning surface area. Now it is, I think, fine. No? Okay, so this is the formula. You need to remember this. Okay. Now, if I just want to calculate the total burned mass of the propellant, the total burned mass of propellant. What is the total mass? So it is the mg, or you can say mp. Okay, and what is the total amount of the total burned mass of propellant? It is mp or mg, it's your choice, and you need to integrate this value m dot g, okay, into up to what time it is burned, up to what time it is burned. Okay, so for that time period you just integrate. Suppose it is burned for you can say 40 seconds, or you can say it is 40 minutes. Okay, so for that time period you just integrate, so you will get that amount of the burned propellant, or mg, no, not dot, sorry, here you just correct this, it is amount of the mass in kg. Okay, in kg, and this value you can take m dot g. What is the value m dot g? Here you have written it is rho p r dot ab. So rho p is the density of the propellant, you can take outside. Okay, and then you just integrate r dot burning rate into ab into dt. So this is the way to calculate the amount of the burn propellant. Okay, sometimes it is asked, you need to find. One time question they had asked, and it was very nice question, mass of the burning rate based question in GATE they had asked. Okay, fine. So this type of according to chamber pressure versus chamber pressure and thrust, we have a time history. Propellant grain can be classified further three types: progressive burning, neutral burning, and regressive. So two types of the three types, and only diagram I will see, I will give to you. So please you just see the diagram and you put in your mind, because sometimes if they have given diagram and they said what type of burning this is. Okay, so how to find this? So progressive means that with respect to time thrust is what increasing. Neutral means with respect to time thrust is not increasing, and this is for the propellant. So I'm just going to give this diagram only. So according to chamber pressure, thrust, chamber pressure, just chamber pressure and thrust versus time history. Time history, propellant grain. ठीक है. Propellant grain can be classified into three types. Depends on these points. For theory point of view, this is very important. Okay, they are asking question. So depend on propellant composition. Point 2, combustion chamber pressure. Pressure PC. Okay, these all points are very important. Initial temperature of solid propellant prior to start, means before going to start, what is the temperature, initial temperature, that also affect on burning rate. Okay, that's the point. Fourth point, combustion gas temperature. Combustion gas temperature. Fifth, very important, it is called velocity of gas flow parallel to the burning surface. Okay, these are few very important points for the burning. Now, final formula I am just going to give based on this numerical they had asked for 2 marks in your exam. It is basically formula given by Wheeler's, and that's the reason it is called as also Wheeler's law. No? And this type of formula called empirical formula. Empirical formulas, that means in basically that derivation you will not have, but through the experiment, multiple experiment, you will develop one relation, and that relation will be here. This relation is what between pressure and burning rate. So after multiple experiments with you will develop one relation between pressure and burning rate. And that's the reason it is called empirical relationship, because we will not have any source of this derivation. I mean, source of derivation in the sense this is not derived formula. This is by the multiple experiment we got this relation between pressure and burning rate. So this final formula I am just going to give you. This is very important. So at at any given temperature. Remember, temperature is what constant for this, okay? At any given initial temperature. So when the multiple experiment they had done, they made initial temperature was constant, only combustion chamber pressure they were changing, and they got the for different combustion chamber pressure they got different burning rate. So they had developed one relation, okay? That's the mean of it. So that's the reason the empirical relation between combustion chamber pressure called PC and burning rate, which is nothing but R dot, okay? R dot. This relation known as Wallis law, okay? So I'll give this relation. So here we are going to talk Wallis law, okay? This is very important. So what result they had given? This result is R dot is equal to A PC to power n, okay? This is the very powerful formula actually, okay? Each and every this meaning of R dot A P C N I will write here, so it will be easy to understand. What is the R dot? It is well known now. It is called burn rate, okay? And why this is also very special, because you need to use this formula with the proper unit, otherwise you will not get correct answer, okay? So this burn rate for this formula will be in millimeter per second, okay? Usually given in millimeter meter per second, okay? R dot. Similarly, we have a PC. PC, you know, it is combustion chamber pressure, but that unit also very important. So the combustion chamber pressure, if you use this formula, so this combustion chamber pressure will be given in megapascal, okay? Remember this. And what is N? So N is the burning rate pressure exponent, okay? The burning rate pressure exponent, or it is sometimes called combustion index, okay? And which is independent of initial grain temperature. I told you initial temperature is what constant, so obviously it will be independent, okay? And the effect of chamber pressure on the burning rate dependent on the constituents of the propellant, okay? So basically whatever the formula you got, it is for constant temperature. That's the mean of it. Next constant we have here A. What is this constant? It is an empirical, it is an empirical constant, sometimes called Wallis constant. Okay, influenced by initial propellant temperature prior to ignition. So initial ignition temperature will be changed, then A can be changed, okay? But for initial temperature, this formula is given. Since this is also constant, it is not going to change. And it is also known as temperature coefficient. Okay, now fine. So and how to, sometimes if it is required to calculate, so how to get this? So basically A is equal to, because it is called temperature coefficient also, so small a is equal to capital A divided by T 1 minus Tp. Generally they will give this value to you, no need to calculate. Here what is the A is the empirical constant, T1 is empirical constant, and what is the Tp? Tp is the propellant temperature prior to ignition. Capital A is constant, okay? Capital A is empirical constant, T is empirical constant, Tp is propellant temperature prior to ignition. Okay, so finally you have this formula R dot, it is A PCN, or also you can write A upon T1 minus Tp Pc to power n. Done. So this burning rate chapter also now over. One more thing, you just add one point. N value is what generally it is less than 1 and greater than 0. Number 1. Number 2. Most propellant, for the most propellant, the value of N. What is the N? I told you it is the combustion index, or it is called combustion index or burning rate pressure exponent. No? So for most propellant, it is N is what, from 0.2 to 0.6. Okay, you just remember this just for information. This is the 0.1 and this is the 0.2. All right. So previous year rocket gate question will solve here. So this is what random problem I have taken, problem 1. Okay, and this problem they had asked in gate, and it is a rocket has and initial mass of 150 kg 150 kg after operation for a duration of 10 seconds. 10 seconds, its final mass is 50 kg. If the acceleration, directly I will write, if g is equal to 9.81, they have given in the problem, 9.81 meter per second square, and thrust produced by the rocket is 19.62 kilonewton. Okay, the specific impulse of rocket is, option they have given to us, it is 400 second, option B 300 second, option C 200 second, option D 100 second. Okay, and this problem is the gate problem, and they had asked gate AE problem, and this problem was asked for 2 marks. Okay, now so see, a rocket has an initial mass means m naught they have given, operation for duration of 10 seconds means t of burning time they have given, its final mass means mf they have given, burnout mass, or mf they have given to us, g 9.81 they have given to us. Okay, 9.81, and thrust produced is what, 19.62, specific impulse ISP. So this is the gate problem. Now you can think, so up to what level we had gone through this subject, and what type of question they are asking. Directly formula based problem I asked many times to you. Just remember the formula. One time derivation is okay, one time whole theory is okay, but every time don't go for it. You just remember the formula. I'm sure this rocket propulsion problem you will solve easily. Anyway, so we'll solve this. So they have given m naught to us. M naught they have given 150 kg. MF they have given to us. What is the MF? MF is nothing but m naught minus MP. If it is required, it's okay. Otherwise, write down just for your revision purpose. M naught minus MP, and this amount they have given to us 50 kg. Burning time they have given to us for 10 seconds. Okay. Now they are saying thrust 19.62 kilonewton. Need to calculate IS. Very simple formula based. Open your box, ISP box. Why I am saying box? Why I am not saying formula? Because in box I have given all the formula related to this. So check what formula will be useful for this given data. As for given data, if you check what formula is what useful. So what I remember, ISP direct formula you can write, and that ISP direct formula was it was ISP is equal to one formula I had given. It was thrust divided by m dot P into Z. This is the formula was given to you. Okay, and that time I told you this thrust formula also is sometimes they will give the weight also, weight flow rate of the propellant. So that time don't get confused. M dot P is nothing but M dot P into G. All right. Anyway, so thrust they have given to us, m dot p they not have given, but we can use this formula and we can get. So what is the mf? Mf they have given to us, and mf is nothing but m naught minus mp. So here you can calculate what is the mp. Mp will be m naught minus mf. You have to see m naught is 150 and mf they have given 50. So 150 minus, I think mf is 50, right? So you can get 100 kg mass of the propellant we have, but in the formula we have m dot p. So what you will do, it is mp, mp not dot. It's actually practice, every time I'm writing dot here, but anyway, it is mp divided by time, burning time of the propellant, you can say. Here this is what burning time, na? Burning time of the propellant. It's not burn rate, it's a burning time, both are different. So mp divided by tv, mp is what, 100, and burning time they have given 10 seconds, so this is what, 10. It is now 10. Now it is burn mass flow rate of the propellant, so it is 10 kg per second. Now ISP directly you can calculate. Thrust divided by m dot p into g. What is the thrust? You can check. It is nothing but 19.62 10 power 3 divided by 10 g they have given to us 9.8. If you calculate, let me find my calculator, 19.62 divided by 10 divided by 9.81 multiplied by 1000. Directly I am getting 200 second. Check what option they have given to us. Option 200 second is C. So your ISP you got 200 second, right? And option, correct option we have is C. This is the first problem. So we'll have another question. This is also gate problems. Problem 2. And this question, if you check, this is nothing but a rocket with lift off mass of 10,000 kg. 10,000 kg moves vertically. Upward. Moves upward from rest. Under constant G for gravitational acceleration, and it is given 9.81 meter per second square. The propellant mass of 8,400 kg burns at constant rate, propellant mass of 8400 kg burns at constant rate, burns at constant rate of 1200 kg per second. If specific impulse, if specific impulse specific impulse of rocket engine is 240 second, 240 second, neglecting drags. Okay, if they said drag, I told you what is the drag loss, neglecting drag. The burnout velocity in meter per second. Option A. What option they have given? 3933.7. Option B. 4314.6. Option C. 4245.9. Option D. 4383.6. 4383.36. Okay, so this is the problem, and this is also gate problem, and this problem you can check that here. I do not have that here, but this is also gate question for 2 marks. Okay, so this type of question again they had asked. It's a very simple formula based problem. Okay, so lift off mass means it is the initial mass. Okay, I will give that naming and all. So solution for this. So lift off mass means mass of the rocket during lift off. Lift off mass, sorry. Lift off mass. Lift off mass means initial mass of rocket, and it is m0. What is this value they have given to us? It is 10,000. 10,000 kg. Okay, and second value, if you check G, they have given obviously 9.8 meter per second square. Then they have given propellant mass 8,400 kg they have given to us. Okay, then next they have given to us that value which is called constant rate of burns at constant rate of 1200 kg per second. So this is the propellant mass of 8400 kg burns at constant rate of 1200 kg per second. So you can say this is the m dot g, 1200 kg per second. Then specific impulse ISP they have given to us. How much? 240 second. Neglecting drag, okay, the burn out velocity. So the find, what need to find? Burn out velocity It is called incremental velocity. It is called change in velocity. These are the different names. And this is nothing but delta V. Done. So based on this, you just open the box, delta V box, change in velocity box, and as per given data, you check what is the delta V. So delta V ISP they have given to us. Check in this problem ISP. So we have formula, and we have formula of first V effective exhaust velocity based formula, and ln 1 upon mr. This is also can write as ISP G ln 1 upon mr. So we have ISP, we'll use that. No? So delta V is equal to, because ISP they have given to us, so we'll use this formula ln 1 upon mr, or you can say ISP G ln what is mr final by initial. So you have delta V is ISPG ln m naught by mf, or ISPG ln m naught, what is the mf? M naught minus mp. Check what data they have given, based on you calculate. I think ISP they have given how much? It's a 240, 9.81 ln m naught initial mass or lift mass they have given to us, it is 10,000. It is divided by m naught 10,000 minus mass of the propellant, it is nicely they have given to us 8,400. If you do the calculation, 10,000 minus 8,400, 10,000 divided by this value, if you take ln of this into 9.81 into 240, it's a 4314. 4314.6 meter per second. Any option they have given to us? 4314. 4314. Nicely they have given option B. This is correct. Huh? So this is the answer, 4314, and correct option you have B. Next problem. So this is what? Problem number 3. And in this problem, the question is a cryogenic. Okay. Cryogenic rocket has a specific impulse of core 55 seconds and characteristic velocity of 2386 meter per second. The value of thrust coefficient for for this rocket is option A. So this is the problem. You just open the box for the characteristics velocity. I had given relation between the thrust coefficient, mass flow rate coefficients, and characteristics velocity, chamber pressure, maximum mass flow rate. All the relation I had given in one single box. So please open that box and relate what data they have given to you. You calculate. So this is the problem. All right, now check. And this is also a gate problem, and it was asked for 2 marks. Okay, this is the gate problem, and it is asked for 2 marks. So now we'll go for the solution of this problem. So solution for this problem is what? Directly formula based. If you remember the formula, you can finish this numerical within second. So if you remember, I had given the formula that characteristics velocity I had given C star, and it was the solution of this problem. So C star they have given to us, and value of C star they have given, it is 2386 meter per second. ISP they have given to us 455 seconds. So based on this we need to find that value. So as we know, we have the formula. You can relate by this. C star we have in terms of combustion pressure POC and ATS, throat area divided by mass flow rate of the propellant. This is the formula 1 for C star. And if you remember, thrust coefficient also I had given CF formula in terms of thrust divided by it was POC, or that chamber pressure what we used. It was chamber pressure PC, POC in the sense total chamber, total pressure or chamber pressure. In the initial only I told you chamber pressure means total pressure. So no need to write each and everything. If you use this 2 formula, we can get the relation, and this relation will be what? CF is equal to, check, it is nothing but thrust divided by PCATH. What is the PCATH? PCATH will be C star into M dot P. And if you check this formula, so if I'm not wrong, then that formula of ISP, it was given thrust divided by M dot P into Z. Now you replace T value, so CF you will have T value will be ISP M dot P G divided by M dot P into C star. This M dot P cancel out. You will have ISP G by C star. Done. You can calculate this. ISP G divided by C star. If you calculate here, 455 I think, no? 455 divided by C star is 2386. 2386. So that CF value you are getting approximate 1.87, because it's a coefficient, so there is no unit. Check option 1.87. This is the correct answer. Option is C. Done. So problem 4, it is given a liquid propellant rocket has the following component masses. Mass of payload ml. How much? 180 kg. Mass of fuel, how much? 470 kg. Mass of oxidizer, how much? 1170 kg. Mass of structure, it is 150 kg. Mass of guidance system, how much it is? 20 kg. Effective exhaust velocity they have given to us, how much? 3136 meter per second. This is called effective exhaust velocity. For this problem, they are asking the velocity increment. Question is the velocity increment. The velocity increment in, check the unit, in kilometer per second we need to find, and this is the fill in the blank problem. Okay, the rocket of the rocket at burnout, while operating in outer space, while operating in outer space. This word they are using so that you can, while operating in outer space, that means all losses, drag loss plus gravity loss will be 0. That's the mean of it. Okay. For this problem, we just check okay. So now check, this is very nice question actually, and this type of theory, because one very big problem we had solved, so nothing to worry. This type of problem easily you can solve. It's very easy only. Okay. Now if I say what is the total mass, then how to get it that? So obviously ml, you can say this is the ml. Okay, guidance system also you can say this is the guidance system here. Okay, and here you will have a propellant. This is what propellant. So propellant you will have here. If I say propellant, so propellant means what? Fuel plus oxidizer, because it's a fuel plus oxidizer. Okay, that you know very well. I am not going to write each and everything, just I will calculate it to direct value. Okay, so for this system, what is the initial mass? I think structural mass also they have given to us. They have given structural mass or not? ms also they have given. So this that body mass you can say, or structural mass also they have given to us. Oxidizer, guidance system, fuel, ML. Done. Now how to start this problem? Simple. You will calculate initial mass. No? So in short, there will go fast, okay, a little bit, because everything we know now. No need to explain again and again. So what is the? We will start from the payload first. Payload ML plus guidance system plus propellant mass plus structural mass. That value you need to write. What is the payload? 180 plus 20. Everything you need to write. 180 plus guidance system 20 plus propellant. If you check how much it is, propellant mass. Propellant means I will write both fuel and oxidizer. So it is nothing but fuel and oxidizer, which is nothing but 470 plus mass of oxidizer 1170 plus mass of structure, it is 150. So if you do this, fine. So if you calculate this, so this is nothing but m naught, and I will use this calculator. So 180 plus 20, 200 plus 470 plus 1170 plus 150. So this value is nothing but 199 kg. This is what initial mass. Okay, this is what initial mass, and they are asking incremental velocity, right? They are asking the velocity incremental means delta v. What is the delta v formula we should have? Delta v is ISP they have given, I think. Effective velocity they have given, so we need to write this formula: effective exhaust velocity into ln 1 upon mr, or you can say we effective exhaust velocity ln initial mass divided by final, and final mass is nothing but m naught minus mp, m naught minus mp. So now we'll calculate initial mass we have. Now we'll calculate m final. What is the m final? M naught minus mp. We have 1990 minus mp is what? This fuel plus oxidizer. So if you calculate m naught minus mp, which is final, so how much you will have? Minus 1170 minus 470. So we have a 350 only, 350 kg, right? Now your problem is solved. What is the delta v? V effective ln m naught is 1990 divided by mf, which is nothing but 350. If you solve this, V effective they have given to us in starting in the problem. How much? 3136. 3136 ln divided by 350. If you do this, you will get 1990 divided by this value ln this into 3136. I'm getting here 5.45 0.23. This is meter per second. But in problem, see what will do mistake, it is fill in the blank, so we'll put this value. No, what they are saying calculate this value in kilometer. So once you fill this data in the blank space, so in kilometer, so this, if you write 5450, so this definitely they will consider 5450 kilometer per second. Computer will accept this answer, 5450 kilometer per second. But what you are getting, 5450 meter per second. So what we'll do, we'll convert it into kilometer, so it will be 5.45 kilometer per second. So in the blank space you have to fill 5.45. that's all. Kilometer per second automatically they will take. You need to fill only 5.45. This is the problem. This is for 2 marks. I hope this one is clear. Done.